Hi everyone, welcome to Lecture 25 Part 1 on Degrees of Belief, Reasoning Under Risk. The objectives for this video are the following. So after watching, everyone should be able to, number 1, explain how we reason under risk, and number 2, calculate subjective utilities from preferences using the first representation theorem, and number 3, calculate subjective degrees of belief from subjective utilities using the first representation theorem. So, this is the first lecture of week 9, and we've moved into chapter 7, which is titled Kinds of Probability. The idea is that the word probability is sometimes used with 3 slightly different concepts in mind when we use that word. The first concept is rational degree of belief, the second is relative frequency, and the third is chance. Now, all 3 concepts obey the rules of the probability calculus that we've developed over the last couple of weeks, but each has a slightly different meaning. The 3 lecture videos this week will look at each concept in turn, and this video's topic is rational degrees of belief, in particular how we recover our degrees of belief so we can work our degrees of belief out given our expected utilities and our preferences. So our journey in this video is to look at the mathematics of reasoning under risk or uncertainty and then state 2 theorems such that when we apply them we'll be able to calculate our degrees of belief given this other information, given our utilities and our preferences. The first theorem will be covered in this part 1 video where we'll look at reasoning under risk, and the second theorem we'll look at in the part 2 video where we look at reasoning under uncertainty. So we're throwing a lot of words round, so let's look at things more slowly. Recall from week 7 that we looked at expected values of wagers, and we said that expected value of a wager is one factor that determines how attractive you find a wager or not. However, we also said that there are other factors that determine how attractive we might find a wager. We talked about how the risk involved in the wager matters, and what real-world value that money has also matters. We said that if you ignore the real-world value that money has, then we say money has constant marginal utility. That is to say, something like $100 is just as valuable to someone who has no dollars as it is to someone who has $1 million. And what we said were that these are not always good assumptions to make. And so the point of this video is to look closer at what happens when we take into account risk and utility, and what happens to the mathematics of expected values. So first, let's unpack what we mean by risk here. The idea is that we are a decision maker who is faced with choices given that they don't know something about the future, and we want to know how we should rationally choose. Now really, there are 2 ways that we might not know something about the future. One is where there is risk involved, and one is when there is uncertainty involved. So I first want to distinguish risk from uncertainty. So let's imagine 2 situations in which the future is unknown. In situation 1, you're betting on a horse race and you don't know which horse will win. And in situation 2, you're betting on the colour of the next card drawn out of a randomly shuffled deck of 52 cards. Now in this second situation, when you're betting on the card, the probabilities are known. Let's suppose, for example, that it's the first card drawn from the deck. Then everyone agrees on the likelihood of a red card. It's 1/2. We can treat this probability as something we can observe, and we might think of it as objective in some sense. And this is what we mean by a situation involving risk. Compare this to the other situation, which I described first, where you're betting on a horse race. Here the probability of the winner is unknown, and unlike the card situation, different people might apply different probabilities to any one of the horses winning. So we can't directly observe someone's beliefs, and therefore we might think of the probabilities in this situation as subjective rather than objective. And we call this a situation involving uncertainty rather than a situation involving risk. For the rest of this video, we're going to focus on reasoning under risk as we've described it here, so the probabilities involved are objective, and then we'll look at reasoning under uncertainty in the part 2 video. Now, consider the following very boring game. Maybe you're playing at the OC County Fair. You flip a coin, and if it comes up heads, you get $20. If it comes up tails, you get nothing. The question is, what's the maximum amount X you'd be prepared to pay in order to play this game? And one approach, as we've seen, is to talk in terms of expected values. So let's look at that in more detail. You've got two options. Either you don't play the game and you for sure get nothing, or you pay X dollars to play the game and you get minus X dollars with probability 1/2, i.e. if the coin lands on tails, you lose the money you've paid to play the game, or you get 20 minus X dollars with probability 1/2, i.e. the coin comes up heads, so you win the $20 and you take off what you paid to play the game. Then the expected amount that you would earn from playing this game is 0.5 times minus x plus 0.5 times 20 minus x, which simplifies to 10 minus x. Now this total expected value is bigger than or equal to 0 just in case x is less than or equal to 10. So what this tells us is that you should be prepared to pay at most $10 to play this game. Anything more than that, you're expecting to lose money. Now historically, this approach to solving the question, what's the most you'd be prepared to play this game, was basically the accepted approach to solving this type of question, until a guy came along, Daniel Bernoulli, around 1738, and he came up with an example that shows, in fact, this is not always a good approach for answering this type of question. And this is known in the literature as the St. Petersburg game. So the St. Petersburg game says this: you flip a fair coin until it comes up heads. If it comes up heads on the first flip, you get $2. If it comes up heads on the second flip, you get $4. If it comes up heads on the third flip, you get $8. And in general, if it comes up heads on the nth flip, you get 2 to the power of n dollars. And so the question, like before, is how much would you be prepared to pay to play this game? So let's try and use the approach we just used, so calculate the expected value of this game. The expected value is 1/2 times $2, plus 1/4 times $4, plus 1/8 times $8, and so on, which is $1 plus $1 plus $1 plus $1 forever. So using the expected value approach, like we did before, that says you should be prepared to pay an infinite amount of money to play this game, and this isn't good. So what's going wrong here, and this is where the marginal utility of money fits into the picture. So let's have a think about another example. Let's say a pauper finds a magic lottery ticket that has a 50% chance of winning $1 million and a 50% chance of nothing. A billionaire offers to buy the ticket off the pauper for $499,999 for sure. So let's pause here for a quick question. According to the expected value method, the pauper should keep hold of the ticket because the expected value in that case is $500,000. But the expected value if the pauper sells the ticket is $1 less than $500,000. So if the pauper prefers the course of action with the higher expected value, that says they should prefer to keep the ticket and reject the billionaire's offer. And this idea seems silly. Why? Because the difference in life outcomes between no dollars and $499,999 is massive for the pauper. Maybe they can afford to eat, go out and buy clothes and so on. Whereas the difference between $499,999 and $1 million is relatively small. You know, maybe they'd be going out and buying a second Tesla or something like that. So the point is that by keeping the lottery ticket, the pauper risks losing an awful lot against gaining relatively little. And so what Bernoulli argued is that people shouldn't be maximizing expected monetary value. That's not how you should solve these questions, but they should instead be maximizing expected utility. And moreover, marginal utility shouldn't be constant like we initially assumed it was in the case of money, but marginal utility should be decreasing. So let's look at that in more detail. We write u of x as the associated utility of an amount x, and the idea is that in the case of money, for example, we might have u of $0 is 0, and u of $499,999 is 10, and u of $1 million is 16. So the increases in utility are not constant here, they decrease as we go up. So now one question we might ask is, what utility function should we use? So let's think about the utility function from the last slide in the case of the pauper example. The pauper should choose the rich person's offer in this situation as long as 1/2 times u of 1 million plus 1/2 times u of 0 is less than u of 499,999. Now if we use the numbers from the previous slide, then the left-hand side of this inequality is 8 and the right-hand side is 10. So if u of x takes those values, the pauper should accept the billionaire's offer if they use this utility function. Now there are, of course, other utility functions that decrease that we might use instead. So what can we say about those? In general, we can say the following. Suppose someone is looking to maximize their expected utility and they have a decreasing marginal utility function. We say in this case that utility function is concave. So they have a utility function that looks like the one on this graph here. Concave means if you draw a straight line between any 2 points on the curve, then the straight line lies underneath the curve. Now if someone has a decreasing utility function like this one, then we say that person is risk averse. It means for them the expectation of utility is less than the utility of the expectation. So let's unpack what I've just said. Along the bottom we've got prizes, so let's consider prizes x1 and x2, and we consider an expectation of the prizes. Let's say 1/2 times x1 plus 1/2 times x2, so an average of x1 and x2. That point is halfway between x1 and x2. And what we're interested in is comparing the expectation of the utilities to the utility of the expectation. Now, the expectation of the utilities is represented by this line here, so it's an average of the utilities of x1 and x2. And on the other hand, the utility of the expectation is just u of the whole expectation itself, so that's this thing, and that's represented by the utility function. And we notice from the graph that the expected utility is less than the utility of the expectation. That's because of the shape of this curve. So if someone has this concave utility function, if they are risk averse, or if they have decreasing marginal utility function, then the utility of the expectation is higher for that person than taking their chances on the expectation of the utilities. So the important thing to know is the shape of this curve, a concave utility function, and what that means, what it corresponds to. So it represents a decreasing marginal utility function, and it means that someone who has a utility function like this one is risk averse. Now the assignments ask you to consider some other utility functions of different shapes, so I will leave this discussion here and we'll move on. So far what we've developed is a little of expected utility theory, which is the workhorse model of choice under risk. The next thing we're going to do is state the first of our big theorems that tells us how we can recover our degrees of belief from our expected utilities when we're reasoning under risk. So to do that, we'll introduce some definitions. We call a lottery a finite list, P1 all the way up to Pn, of probabilities such that they all add up to 1. So for example, 1/2, 1/2 is a lottery, and so is 0.3, 0.4, 0.3. Now we think of lotteries as being defined on a finite set X of prizes, so that you might have something like 50% chance of winning an apple or 50% chance of winning a banana. And the prizes in that case would be the apple and the banana. So your set X would consist of apple, banana. Now we assume we are someone who has a way to compare lotteries. And what this means is that we have a relation, curly greater than or equals to, on lotteries. And if P and Q are lotteries, we read P curly greater than or equals to Q as we prefer P to Q. And then the theorem says this: let X be a finite set of prizes and curly greater than or equals to be a binary relation on the set of lotteries on X, so we can compare two lotteries using that relation. Then curly greater than or equals to satisfies these conditions Vnm if and only if there exists a function u from x to the real numbers r, such that for any lotteries on X, we prefer P to Q if and only if the expected utility of lottery P is greater than or equal to the expected utility of lottery Q. Now, there's a lot going on here. VNM is a list of conditions that your preferences have to satisfy in order for the conclusion of this theorem to go through. VNM stands for von Neumann and Morgenstern, to whom these conditions are usually credited. Now, we won't be concerned with what the conditions are in this course, so you won't have to know them for assignments or tests, and we're just going to assume they hold in all the examples that we look at. Instead, it's the conclusion of the theorem that we're most interested in, and so we're not going to prove the theorem either because it's a bit beyond the scope of this course. Instead, we're going to focus on how to apply this conclusion. So we'll call this the first representation theorem. It's a representation theorem because it represents our preferences as rational agents as expected utilities. And its import is this: we don't need to know someone's attitude towards risk in order to predict how they will choose between two risky alternatives, because all they're going to do is act as if they are maximizing expected utility. Okay, so we've said a lot. Now let's look at an example of how we apply this theorem and ultimately how we recover our degrees of belief from utilities. That's what we're interested in taking away from this lecture video. First, we're going to look at objective 2, which was how we recover utilities from preferences, and it will be very useful to have a good grasp on this example. So here's the example. Let's suppose I'm a farmer and I'm faced with a decision problem. And let's suppose I want the following things. I want a horse, a goat, a sheepdog, and a cow. Now, my current decision, let's assume, is structured so that I get exactly one of these from my decision. Now, let's suppose I rank how much these things mean to me. So the thing I want most is a sheepdog, followed by a goat, followed by a horse, and finally followed by a cow. Now we consider the following two pairs of lotteries. Option 1, in which we have two lotteries, A and B. Lottery A says that I get a sheepdog with probability 0.8 and a cow with probability 0.2. Lottery B says that I get a goat for sure. And here's the second option. We have two lotteries again, C and D this time. Lottery C says that I get a sheepdog with probability 1/2 and I get a cow with probability 1/2. And Lottery D says that I get a horse for sure. Now notice that we are assuming that the lotteries are objective here, so the probabilities involved in each one are objective, and that means we're indeed reasoning under risk. So let's suppose further that I am indifferent between Lottery A and B, and I'm indifferent between Lottery C and D. So what that means is that I prefer Lotteries A and B equally, and I prefer Lotteries C and D equally. Now we can use the first representation theorem to calculate my utility scale. So what we're doing is recovering my utilities from my preferences about these lotteries here. So how do we do that? Well, let's consider lotteries A and B first. Now because I'm indifferent between them, I prefer them equally. So by the representation theorem, if I'm maximizing expected utility, then I assign the same expected utility to each lottery. The expected utility of lottery A is this, 0.8 times U of sheepdog plus 0.2 times U of cow. The expected utility of lottery B is this, 1 times U of goat. So by the representation theorem, I know that 0.8 times U of sheepdog plus 0.2 times U of cow is equal to 1 times U of goat. Now let's look at lotteries C and D and say something similar about those ones. Because I'm indifferent between them, I prefer them equally. So by the representation theorem, if I'm maximizing expected utility, then I assign the same expected utility to each lottery C and D. And well, the expected utility of lottery C is 0.5 times U of sheepdog plus 0.5 times U of cow, and the expected utility of lottery D is 1 times U of horse. So, by the representation theorem, I know that these things are equal, so 0.5 times U of sheepdog plus 0.5 times U of cow equals 1 times U of horse. Now, because my decision problem is structured so that I end up with exactly one of these animals, what we can do is scale the utilities and put them on a scale from 0 to 1. This simplifies things for us. So we'll say that U of sheepdog is 1 because that's the thing I wanted the most, and U of cow is 0 because that's the thing I wanted the least. Now, if we substitute these values into the equations we've just derived using the expected utilities of lotteries A and B, this one, then this reads 0.8 equals U of goat. So what we've done is worked out or recovered my utility on getting a goat. And we've done this using our preferences about lotteries A and B. And similarly, if we substitute those values into the equation we derived using the expected utilities of lotteries C and D, so this one, then this equation becomes 0.5 equals U of horse. So again, we figured out what my utility on getting a horse is from my preferences about lotteries. So, put all that together, my utility scale is this. U of sheepdog is 1, U of goat is 0.8, U of horse is 0.5, and U of cow is 0. So this is what Objective 2 focused on way back at the beginning. We've used the first representation theorem to recover my utilities from my preferences about lotteries. And the idea is this is useful to us because in everyday language we talk in terms of preferences about lotteries. So you'd say, oh, I prefer this to this, or oh, I'd take either one with equal preference. Now these utilities that we've recovered are called subjective utilities because they were determined by my preferences, and I can no doubt be wrong about what's good for me, but they are just the preferences I have. Now let's move on and look at an example that addresses the third objective, so recovering degrees of belief from subjective utilities. So let's suppose I'm a farmer again, but this time let's simplify things and suppose I'm just interested in getting a horse. So I've sought out a wager in which I either win a horse or I don't win a horse. So let's suppose there's a bag with red, yellow, blue and green balls in it, but I don't know how many of each. And the wager is such that if I buy a ticket on a red ball and a red ball is drawn, I win a horse, otherwise I win nothing. And similarly for the other colours. So if I buy a ticket on a blue ball and a blue ball comes out of the bag, I'll win a horse, otherwise nothing, and so on. Then the best thing for me in this situation is to win a horse. So the utility of winning a horse here is 1, or U of horse equals 1. And similarly, the worst thing for me in this situation is to win nothing. So the utility of winning nothing is 0, or U of nothing equals 0. So we consider then the following two pairs of lotteries. Option 1, in which we've got two lotteries A and B. Lottery A is keeping a ticket on a red ball for sure, and Lottery B is an objective lottery ticket with a 20% chance of winning a horse. And option 2, in which we've got lotteries C and D. Lottery C is keeping a ticket on a blue ball for sure, and Lottery D is an objective lottery ticket with a 25% chance of winning a horse. Now notice again that we're assuming that the lottery tickets are objective here, so the probabilities involved in each one are objective, so we are indeed still reasoning under risk. Let's suppose further, like before, that I am indifferent between Lottery A and B, and I'm indifferent between Lottery C and D. So I prefer Lotteries A and B equally, and I prefer Lotteries C and D equally. Then using the first representation theorem, I can calculate my utility scale. So again, we're recovering utilities from preferences here. So how do we do that? Well, let's consider Lotteries A and B first. Because I'm indifferent between them, I prefer them equally. So by the representation theorem, if I'm maximizing expected utility, I assign the same expected utility to each lottery. The expected utility of Lottery A is this, U of keep my ticket on a red ball. The expected utility of Lottery B is this, 0.2 times U of horse. So by the representation theorem, I know that these are equal, and so U of keep my ticket on a red ball is equal to 0.2. Because remember, U of horse is just 1. Now we do a similar thing for C and D. So because I'm indifferent between lotteries C and D, I prefer them equally. So by the first representation theorem, if I'm maximizing expected utility, I assign the same expected utility to each lottery. The expected utility of lottery C is U of keep my ticket on a blue ball, and the expected utility of lottery D is 0.25 times U of horse. So by the representation theorem, these things are equal, and so U of keep my ticket on a blue ball is 0.25, because again, remember, U of horse is just 1. So we've got our utilities from our preferences. Now we're going to recover our degrees of belief from the utilities. So how do we do that? Well, we think for a second, and it turns out we know something about U of I keep my ticket on a red ball. We know that U of keep my ticket on a red ball is equal to degree of belief that a red ball is drawn times U of horse, plus 1 minus degree of belief that a red ball is drawn times U of nothing. So D of B here stands for degree of belief. We could just as well write P, of course, for probability, but I want to be explicit that we're talking about degrees of belief here. Now, since U of keep my ticket on a red ball is 0.2, that's the utility we just recovered, this means degree of belief that a red ball is drawn times U of horse plus 1 minus degree of belief that a red ball is drawn times U of nothing is 0.2. But since U of horse is 1 and U of nothing is 0, this reads degree of belief red ball is drawn is 0.2. And that says that my degree of belief in a red ball coming out of the bag is equal to 0.2. So we have recovered my degree of belief from my subjective utility here. And because the utility is subjective, we call this my subjective degree of belief in a red ball being drawn. So we can do a similar thing in the blue case. What we realize is that we know something about U of keep my ticket on a blue ball. We know that U of keep my ticket on a blue ball is equal to my degree of belief in a blue ball being drawn times U of horse plus 1 minus degree of belief in a blue ball being drawn times U of nothing. And since this is what we figured out before, U of I keep my ticket on a blue ball is 0.25, what this means is that degree of belief in a blue ball being drawn times U of horse plus 1 minus degree of belief in a blue ball being drawn times U of nothing is 0.25. And then we substitute the values in again. So U of horse is 1, U of nothing is 0. So this reads, my degree of belief in a blue ball coming out of the bag is equal to 0.25. So again, we have recovered my degree of belief from my subjective utility here. And again, because the utility is subjective, this is a subjective degree of belief. It's my subjective degree of belief that a blue ball will be drawn from the bag. So let's pause for breath. What have we seen? We've seen how, when we reason under risk, our degrees of belief are calculated in terms of expected utility. So expected utility theory is how we reason under risk. And we've seen that if we have preferences over lotteries that satisfy the conditions, which remember we don't need to know what they are, we're just assuming that they hold in this course, then just using our preferences alone, we can figure out our subjective utilities, and in turn we can figure out our subjective degrees of belief. And what this means is that we can predict how people will choose under risk, even if we don't know how they feel about risk per se. All we need to know are their preferences. So the most important things to know from this video are what the shape of the utility function means in terms of your attitude towards risk, how to recover subjective utilities from preferences using the first representation theorem, and in turn how to recover subjective degrees of belief from subjective utilities. So make sure you can follow the examples that we've been through in the video. Okay, so in the next installment we'll look at how we reason under uncertainty rather than risk, so when the probabilities are subjective instead of objective like they have been here. So have a go at your self-reflection questions, and I'll see you all next time.